For the reactions in section 13.6, we're going to be talking about three-membered ring intermediates that act like carbocations, but they're not full-out carbocations. These reactions, this first reaction is an oxymercuration demercuration, and this is actually going to give us the same transformation as adding H2SO4 and water to an alkene, so that hydration reaction. It's going to give us that same transformation and the same type of product, which is the Markovnikov product, but we're going to be able to do this in milder conditions, and the best thing is we won't have a carbocation. As we've seen in some of the previous videos, when we do get carbocations, we could have hydride shifts or methyl shifts, so these rearrangement reactions, and that can mess up what product we actually want to get. And so using these conditions a little bit milder in general, adding H2SO4, that's a pretty strong acid. Depends on what else you have in your molecule, it could react. And so these conditions give a little bit milder way to do that same transformation. For this one, we're going to be adding our alkene with HGOAC2 and water, and then we're going to be in a separate step adding NABH4. So the first step is going to be where we do the oxymercuration because we get the oxygen and the mercury added across the double bond, and then we do our demercuration where we take the mercury off and replace it with a hydrogen because we don't want that mercury on there. For our mechanism, the first step is going to involve one of the groups that are attached to the mercury, in other words, one of the ligands disassociating from the mercury. So that's going to give us this compound here, and this is a good electrophile. You can start your mechanisms at this point. You don't necessarily have to show this happening. As long as you know that this is formed, you can start here. And what's going to happen is going to look similar to how we were doing the other reactions with the carbocations, where the double bond's going to come and attack. But with these atoms, we're going to see now in this section, they're going to be large enough that they're going to be able to attack back. So we're going to be using the lone pairs on that mercury to go and attack back. This is going to make a three-membered ring that looks like this. And we're going to have, if we want to see kind of what's going on with the electrons, we're going to have the lone pairs of the mercury. They're making this bond here, and the electrons that were in the pi bond are actually making the other bond of the ring. It can be sometimes hard to see these three-membered ring intermediates, especially at first. So this is what's going on with our mechanism. We get to this three-membered ring, and unlike with a carbocation, it's not immediately clear where is the nucleophile going to attack. We have these two carbons that used to be involved in the double bond. Now they're both attached to mercury. One of them is able to be attacked easier than the other. To take a look a little bit more closely at this intermediate, we actually see that this bond from the mercury to carbon 1 in this case is actually longer than the others. So really that bond is kind of more like a partial bond. And that's because the delta plus on that carbon of the that used to be in the double bond, is actually more substituted. And so that delta plus is easier able to be held on that more substituted carbon because you have these groups helping to stabilize that delta plus. The carbon 2, the one from over here, this one does not have that same hyperconjugation, and so it can't help hold that delta plus. And so the mercury pulls more away from the more substituted carbon than it does from the less substituted. And so that leaves us a delta plus here. And this is going to be the same phenomenon in all the reactions we're going to see in 13.6. So it's very important to understand that that delta plus is on that more substituted carbon, even though we do have this three-membered ring. And so we're talking about partial charge, not a full out positive charge, but we are still going to have it on the more substituted carbon for the same reasons. Continuing now with our mechanism, our more substituted carbon, we're always looking out for when we make these three-membered rings. Carbon 1 is more substituted because it's attached to 3 total carbons. Carbon 2 is only attached to 1. And so we're going to go ahead and attack carbon 1 and break open that ring. So we're going to have our oxygen attached to where carbon 1 is. And then we broke open the ring, and so now that mercury is not attached to carbon 1 anymore. It's gone, but it's still attached to carbon 2. The last thing we have to do for this oxymercuration step is we do have to alleviate the charge because we do have a positive charge on that oxygen once it goes to attack. So we can use another water molecule to come and take off one of the H's. And that's going to give us our oxymercuration product with that OH on the more substituted position. For what happens next, we don't necessarily have to show a mechanism for this. It's a little bit more complex. Before the demercuration, all we have to know is that this compound replaces this bond to the mercury with a bond to an H instead. So then we can just go ahead and draw that out. And so overall, with the oxymercuration, that's how we get the oxygen on across the double bond, and that goes to that more substituted position, just like it did when we added acid in water. So this one, the OH goes to the more substituted position, and then we just need a separate step to then put the H on because we weren't using acid to get it on in the first place, so we wouldn't already have it on. We actually have the mercury on there instead. So we do have to replace that with an H, and that's going to give us our final product where we've added water across the double bond in this case, but we've done so in a Markovnikov fashion, and we also have our mechanism has gone through this three-membered ring. So these three-membered ring intermediates are going to be very important for 13.6, and we're always looking for that more substituted position to attack. This is a little bit counterintuitive if you're thinking in terms of sterics. We are not explaining this in terms of sterics because we were explaining it in terms of electronics. So that delta plus, this is going to be overriding any steric considerations in this reaction. So be sure to keep that in mind.